I have built a portable capacitive discharge spot welder, which can be used to attach nickel strips to battery packs. This device can be powered with USB-C power banks and has adjustable voltage and pulse energy. This design uses mostly off-the-shelf components without custom PCBs. I used a capacitor bank made of 19 low ESR capacitors, a second-hand industrial Thyristor module to switch the welding pulse, a step-up converter used to charge the capacitors, a potentiometer and voltmeter to adjust the voltage, a slightly modified relay module used to trigger the welding pulse, USB-C power input, trigger connector, and welding output. Part numbers, detailed schematics, and additional files are linked in the description. No microcontrollers or programming skills are required. I did some test welds on coin cells and AA cells, and these welds were pretty strong and definitely usable. I was able to hang 1 kilogram or 2.2 pounds of weight on the nickel strip without any problems. To remove the strip from battery, I needed to use pliers and apply quite a bit of force. Some pieces of the nickel strip remained attached to the battery, which means that they were properly welded. This is an animation showing how the circuit works. Here we have a charged capacitor bank. In order to make a spot weld, we need to dump all of its energy into the nickel strip in a very short time. The process starts when the trigger button is pressed. We can see that a small timing capacitor is quickly charged now. After a certain voltage threshold is passed, a pair of relays will be activated. The first relay is used to stop capacitor charging. This is important because we are using a Thyristor to switch the welding current. And a Thyristor, once activated, will stop conducting only after there is nothing more to conduct. Therefore, the charger must not be connected when welding happens. Otherwise, welding would never stop, since capacitors would be continuously charged. The second relay is used to discharge a small capacitor into the gate of the Thyristor. This provides a single short pulse which activates the Thyristor. After the Thyristor has been activated, the energy stored in the capacitors will be released into the nickel strip, creating a short spike of hundreds or thousands of amps and making a spot weld. This happens really quickly in real time. The timing capacitor, which has been charged when the trigger button was pressed, will create an additional delay of around 1 second before the capacitor bank will start being recharged again. This is required to make sure that the capacitor bank has been drained completely and the Thyristor got deactivated. I started by soldering capacitors to a perf board using parallel connections. I also used a copper wick to enhance the current carrying capacity. I used 19 Nichicon UBY automotive-grade low ESR capacitors. Each of them was rated at 35 volts, 7500 microfarads, and 18 milliohms ESR. That gives 142,000 microfarads of total capacity and over 68 joules of energy when charged to 31 volts, leaving few volts of safety margin. I soldered a couple of bleeder resistors, which will slowly discharge the capacitor bank when it's not used. I also soldered thick cables to the positive and negative sides of the capacitor bank. I soldered a wire lug to the negative cable. This cable will later be attached to the Thyristor module. The positive cable will be attached directly to the positive terminal of the welding connector. I also prepared an additional short cable, which on the one side will be attached to the Thyristor and on the other side will be attached to the welding connector. I used a high current XT90 connector for the welding wires. I soldered a pair of thick and flexible silicone wires to copper welding electrodes. I used a few pieces of heat shrink to insulate the electrodes. Only the tips need to be exposed. Now I am adding a small trigger button, which will be attached directly to one of the electrodes. I'm also covering the electrodes with some rough textile wire bonding tape, which will make for a better grip. I'm securing the button with additional pieces of heat shrink and tape. This is how a complete set of electrodes should look like. The trigger button is connected to a barrel jack, and welding wires are terminated with an XT90 connector. Now I need to modify the relay module. This is how the wiring should look like. Now it's time to modify the step-up converter. This will allow the voltage to be adjusted with an external potentiometer with the range of around 16 to 31 volts, which corresponds to pulse energy between 16 joules and 68 joules. I designed and 3D printed a front panel which fits into a universal enclosure. Even without a 3D printer, it should be fairly easy to make a custom case out of a plastic container. Now the modules need to be wired in the way shown in the picture. If you want to see a fully detailed schematic, please check the description of this video. After wiring everything up, all of the components can be inserted into the enclosure. And now the spot welder is ready to be used. To make a spot weld, a nickel strip needs to be pressed firmly by both electrodes. And after capacitors are fully charged, the trigger button needs to be pressed. Please remember to do your research about safety precautions when handling and spot welding batteries, especially lithium-ion cells. This spot welder is portable, therefore it's possible to operate it outdoors to minimize any potential risks.